We'll get started. People will dribble in and out as they often do in Zoom calls. I'm truly delighted to have Katie Jenkins with us today. Moved up in the schedule from a couple of weeks from now. So if the talk is less than fully baked, which I expect it won't be, it's because we changed the schedule on her at the last minute. Katie is presently a postdoc at Northwestern. She works in bioelectronics and personal wearable health thingies, and everybody else in the room probably knows more about this stuff than I do. So I'll stop talking, and Katie, go ahead and introduce yourself.
Yeah, thanks so much. Yeah, as you said, I'm at Northwestern currently. I'll get my slides up. Yeah, I'm at Northwestern currently, and then today I'll just be talking about like my kind of vision moving forward in my research, as well as what has motivated me throughout all of my research that I've been a part of. So I'll just go ahead and get started. Yeah, I'm really excited to present today on my research and vision working toward on-body health monitoring and highly personalized medical treatment. As we're all pretty familiar with, current health monitoring and treatment involves typically making an appointment, which could even be months in the future, going to your doctor, and then your health team running tests and exams to diagnose health conditions. In addition to being time-consuming and costly, this type of analysis only provides a single snapshot of a person's condition, and typically follow-up tests and appointments are needed. But health treatment doesn't have to be this way. Instead, utilizing soft, wearable devices to monitor health conditions and record clinical quality data, which doctors can remotely analyze, enables fewer physical visits to the doctor, lower costs, and the addition of predictive algorithms like machine learning will enable analysis of the data to lead to earlier detection of diseases and improved health of patients overall. Additionally, even for in-hospital treatment, utilizing wearable devices instead of currently used wired measurements can improve treatment for patients. For example, for newborns, wires can really prevent and frustrate skin-to-skin parent-child interactions. And we know that skin-to-skin contact is so vital for infant development and health. So getting rid of those wires opens up a better treatment for infants in the NICU. So the future of health monitoring using wearable devices is extremely promising. But what is the current state of wearables? So there are many conventional wearable electronics, which are quite impressive. However, they all share a fairly similar engineering paradigm. In general, it's a rigid block of electronics, usually heavy and planar, and typically loosely coupled at the skin or near the body. And these are really great for measuring steps or activity, and maybe even an assessment of a person's sleep activity. But the lack of having an intimate interface with the body really frustrates the reliable collection of clinical quality data, and additionally limits these devices from providing more useful and detailed information about our health on a more molecular level. So I see this as both a challenge and opportunity for my own research to create more body conformal wearable devices with enhanced physiological monitoring to provide more detailed health information. So to achieve this goal in designing wearable or implantable biodevices, broadly, there are three areas that need to be controlled simultaneously in these wearable or implantable devices. And those areas are the materials, the electronics, and/or the sensing, and importantly, how does the device interface with the body? For example, conventional silicon electronics are hard and brittle, which need to be modified to be able to be used on high curvature surfaces that are present on or inside the body. Additionally, the interface with the body is exceptionally important, as devices need to be in intimate contact with the skin to measure biosignals, but must be able to be removed gently enough to prevent injury to fragile patient skin. So achieving this simultaneous control has been the focus of my PhD and my postdoc, and is the ultimate goal of my future research. So in my talk today, I'll discuss my postdoctoral work with Professor John Rogers at Northwestern University, focused on the development of novel switchable adhesives to use with wearable electronics. Then I'll outline some of the accomplishments during my PhD with Professor Mike Arnold at the University of Wisconsin-Madison, where I studied carbon nanotube assembly from solution and developed techniques to align carbon nanotubes across the wafer scale, which enabled high-performance logic and RF electronics, as well as promises to enable high-performance wearable devices. Finally, I'll briefly discuss future research directions to develop novel bioengineering technologies for improved patient treatment and earlier diagnosis of diseases. First, I'll focus on my postdoc work. So currently, strong adhesives are needed in medical treatment and continuous health monitoring, and must be used to attach things like bandages, electrodes and wires, or even wearable devices to the patients to continuously monitor those biosignals. And removing these strong adhesives after measurement can cause mild skin irritation for healthy adults, but more seriously can cause injuries and subsequent infections in populations with fragile skin, such as neonates and the elderly. The work I'll present here focuses on the development of a controllable adhesion reduction layer to interface wearable devices with the body. So shown at left is the architecture of a typical wearable health monitoring device, where the first 5 layers from the top are just related to the device itself. The work I present here focuses on the development of this controllable adhesion reduction layer, which we use to attach the device to the body. And here we envision the adhesive layer to be single use so that we can easily attach it and remove it from devices after measurement, which helps to prevent cross-contamination between patients. As with anything that interacts with the body, there are some design constraints that we had to keep in mind when developing this thermally triggered layer. First, the adhesive should remain intact at surface body temperatures, which do vary across the body, but in general range between 33 and 37 degrees Celsius. Additionally, based on thermal exposure guidelines, we take 1 minute at 51 degrees Celsius as the temperature and time limit for these adhesives. So that means that the adhesion reduction should be triggered in a fairly narrow range of 40 to 50 degrees Celsius. And importantly, all of these materials need to be biocompatible and skin safe. So with these constraints in mind, the adhesives I developed are based on architectures of crystallizable oils, which are just oils that are solid at room temperature, and adhesive silicones. So I devised a scheme to embed these oils in silicone matrices and attach this architecture to the body with a skin-safe adhesive. So during normal device operation, the device is attached to the skin in a strong adhesion state. And then by applying mild heat, such as using a heating pad or using a resistive heating circuit, above the oil's melting temperature, the oil melts and diffuses through the adhesive. And then the oil, after it diffuses through the adhesive, collects at the interface between the adhesive and the skin and acts to reduce the adhesion of the device, in some cases making the device fall off of the body. And importantly, all of these materials are biocompatible and used in commercial skincare products, as well as drug delivery research. So here we study the effect of integrating the crystallizable oil into silicone matrices in 2 different architectures. The first I'll discuss is randomly distributed oil crystallites throughout the entire thickness of the adhesive composite material. And this is just obtained by mixing melted oil into uncured silicone and then spin coating. So in this first architecture, the oil is distributed throughout the entirety of the adhesive. In this second architecture, we instead embed the oil as these patterned circular discs near the surface of the composite, filled using a discontinuous de-wetting procedure, which I'll discuss more later. First, though, we'll study the randomly distributed oil crystallites. So shown here is a plot of adhesion energy versus amount of 1 pentadecanol, which is a crystallizable oil, dispersed in an adhesive silicone, Ecoflex gel. So here the blue data is measured at room temperature and the red data is measured at temperatures above the melting point of the oil. And we can see that above a 10 weight% oil loading, we achieve over a 75% adhesion reduction. Similarly, for 1 pentadecanol in a different adhesive silicone with initial stronger adhesion at room temperature, we're able to achieve greater than a 50% adhesion reduction. And in both of these plots, the solid and dashed lines correspond to analytic models developed by our theoretical collaborators that take into account the relative surface area, the adhesion of the solid or liquid oil, and the adhesion of the silicone itself. And we can see that these models match the experimental data well, which provides more detailed insights into how these adhesives function. In addition to a large reduction in adhesion, it's also important that the adhesives remain firmly adhered to the skin until thermally actuated. So here I measured adhesion energy as a function of temperature, and below the melting temperature of the oil, the adhesion energy remains fairly constant. However, above the melting temperature of the oil, the adhesion energy decreases by approximately a factor of 3, so that the wearable device can be removed safely. And this sharp drop in adhesion at specific temperatures is vital to ensure that the device remains on the skin during measurement and can be removed quickly, limiting the thermal exposure to the skin for a patient. Studying this random oil crystallite composite demonstrates the inherent underlying phenomena and that this thermally switchable adhesive works as we would like it to. However, we next study the effect of the oil in a more systematic method by patterning the oil in a thin, flexible layer deterministically. So to study the effect of oil loading in a deterministic method, I fabricated adhesive composites comprised of embedded crystallizable oil discs in a silicone matrix, and then coated that with an adhesive silicone layer to interface it with the skin. To create these embedded oil discs or payloads, I used discontinuous de-wetting to fill pre-patterned recesses in this silicone backer with the liquid oil. So in this process, the liquid oil travels along the mold and the liquid pins on the edge of the wells due to structural heterogeneity. But if the energy is chosen correctly between the oil and the silicone, then the bulk liquid continues to move across the oil or across the silicone until a drop ruptures and it fills each of these individual wells. This technique enables high fidelity filling of oil wells across large areas. Shown here are 50 micron diameter wells. You can also fill oil wells of different diameters as well. So these patterned oil architectures allow us to systematically study the effect of oil amount on adhesion reduction. So shown here is a plot of adhesion energy versus well spacing, where the blue data is measured at room temperature and the red data is measured above the melting temperature of the oil. And we can see that there is a greater adhesion reduction as we pack more oil wells closer together at a set well diameter. We also see a slight increase in adhesion reduction with increasing well diameter at a set spacing. However, regardless of varying diameter or the spacing, the adhesive force reduction is just related to the amount of oil embedded. So shown here, the blue data corresponds to 1-pentadecanol, a fatty alcohol, and the red data is N-docosane, a linear alkane, where both are crystallizable oils. And these closed markers are room temperature, and the open markers are above the melting temperature of the oil. So we see that regardless of oil type, as long as the area covered by the wells is greater than about 30%, there is a 75% reduction in adhesion upon heating. And again, these dashed lines correspond to analytic models developed by our collaborators, which also closely match the experimental data. Additionally, we use 3D confocal laser reflectance microscopy to confirm the oil configuration before and after heating. Shown here is the 3D reconstruction of the oil before heating, where the oil, which is plotted as this green color, is embedded in the silicone wells below a layer of adhesive silicone. After heating, the oil has melted from the majority of the wells and has diffused through the interface layer to reduce the adhesion at the skin, as quantified in the adhesion measurements that I showed previously. This adhesion reduction was exciting. However, we also had to confirm that these adhesives do not interfere with wearable device measurement. So here we used our thermally switchable adhesives to attach wearable devices, including the near-infrared spectroscopy or NIRS device for measuring brain function and oxygenation, the mechanoacoustic or MA sensor for measuring motion tracking and monitoring vibrations associated with heart sounds and respiration, and also an electrocardiogram or ECG device for assessing cardiac health. So first, shown here is the 3-channel accelerometer output from the mechanoacoustic device attached at the suprasternal notch. As seen, accelerations in the direction perpendicular to the surface of the skin, or here the Z direction, show cycles of expansion, and contraction that occur of the chest during normal breathing or resting, as you can see during the first 25 seconds and the last 50 seconds. You can also clearly determine the difference between different actions taken by the subject during measurement. Measurements of reflectance mode photoplasmograms, or PPGs, captured from the forehead confirmed operation of the NIRS device as well. So measured with the patient at rest, 8 cardiac cycles occur within 10 seconds, corresponding to a heart rate of 48 beats per minute. And then finally, we use temperature switchable adhesives to replace the bulk adhesives used to attach the ECG device to the skin. And so here we've cut openings in the thermally switchable adhesive to allow use of a conductive hydrogel at the electrode locations. And the resulting data signals of all of these devices are comparable to those obtained with standard adhesives and indicate that our thermally switchable adhesives do not interfere with device measurement. So while these switchable adhesives can be activated by external means, such as through applying a heating pad, wireless modules that integrate directly into the existing wearable device architecture provide a much more convenient and controlled mode of adhesion reduction. So shown here is a schematic and image of a resistive heating device that we developed to achieve wireless heating control, where the solid and flexible components are mounted on islands connected by these flexible trace bridges, which allow the device to flex and deform on high curvature patients, such as neonates. Applying voltage across the resistive heating material results in a uniform temperature across the heating area, as shown by this IR image. And then we also determine that the temperature corresponds linearly with applied power density, enabling the precise control over applied temperature. And then here we also insert the heating module that we developed directly within the mechanoacoustic device encapsulation to yield a single integrated system with wirelessly controlled adhesion to the skin. And so here the flexible PCB of the resistive heating module folds around that of the mechanoacoustic device and is powered by the same battery. So then again, mounting it at the suprasternal notch of a healthy subject yields 3-axis accelerometry measurements, which confirm the quality of the data. So to summarize, in my postdoc, I developed a strategy for skin-safe thermally switchable adhesives based on biocompatible crystallizable oils and adhesive silicones. These adhesives demonstrate over a 75% adhesion reduction upon thermal activation, enabling adhesives and devices to be removed safely from patients with fragile skin. And then finally, the development of a resistive heating FPCB and integration of these adhesives into different wearable devices demonstrates the broad utility of these adhesives into different health monitoring applications.
So just a quick question, Katie, are these adhesives reusable, or is this a one-time?
For these are typically one use, just because, well, we designed them kind of with the goal of one use because we wanted it to be use it on a patient, take the device off, remove it, and then you don't have to worry about cross-contamination between patients. For some of the bulk adhesives, like the non-patterned ones, there's enough oil within the entire bulk of the adhesive. So you can use it multiple times, but usually it's only like 2 times before the adhesion decreases, enough at room temperature that it won't adhere to the skin anymore. Did that answer your question?
Yeah, thanks, great.
So while the wearable devices I explored in my postdoc work are still based on conventional electronic materials like silicon, next I'll discuss my work focused on instead re-engineering the semiconductor electronic components themselves to utilize next generation materials for improved electronic performance and functionality. So in my PhD, this focused on utilizing carbon nanotubes for post-silicon nanoelectronics. So carbon nanotubes, they're one of the most exciting semiconducting materials ever discovered. They exhibit tunable band gaps roughly inversely related to their diameter, which enables their use in a variety of different electronic applications. Importantly, charges also move extraordinarily well through carbon nanotubes, for example, exhibiting ballistic conductance near the theoretical limit, which enables fast transistors with high drive currents. Additionally, their one-dimensional nature and small dimensions enable excellent gating or excellent control over turning the device on and off, even as devices continue to aggressively downscale to dimensions to only a few nanometers in size. Nanotubes also exhibit high mechanical resilience, which enables their use in flexible and stretchable electronics, unlike traditional brittle semiconducting materials like indium tin oxide or bulk silicon. So with all of these exciting properties, the question then becomes, why don't we have commercial carbon nanotube electronics yet? And there have been two major materials challenges that have faced the integration of carbon nanotubes into electronics. First, carbon nanotubes are produced in heterogeneous mixtures of both semiconducting and metallic nanotubes, which kind of look like this black powder shown here. These mixtures must be preferentially sorted to eliminate all metallic carbon nanotubes and select only purely semiconducting carbon nanotubes with similar band gaps. If you have a metallic nanotube then in a transistor, then you won't be able to turn that transistor on and off. So you have to eliminate all of the metallics. And then second, carbon nanotube, and then the second challenge has been able to align carbon nanotubes to fully exploit their exceptional charge transport properties. As unaligned nanotubes reduce drive current and crossing nanotubes increase variability in the off state, which leads to non-uniform circuit performance and increased power consumption. So there have been a lot of great work focused on overcoming this challenge of isolating purely semiconducting carbon nanotubes. So that challenge is fairly solved. But the remaining challenge of alignment has really frustrated the field of carbon nanotube electronics and prevented the integration of this material into industry-produced devices since their discovery in 1991. But if these aligned nanotube arrays can be produced, nanotubes promise to lead to faster, more power-efficient semiconductor electronics for applications including high-performance computers and logic, where carbon nanotubes promise a 5 times current density as well as lower power consumption than currently used silicon. As well as thin film transistor applications and flexible electronics for devices such as biosensors or printed electronics. Due to their exceptional charge transport mobility, in these applications, nanotubes promise to exceed current drive, energy efficiency, and sensitivity of commonly used amorphous oxide semiconductors in these applications. Significant progress towards these goals has already been achieved, and random unaligned nanotube films have recently been integrated into a clean room fab environment, headed by researchers at MIT and funded by a $60 million DARPA grant. So a tremendous amount of work is still being funded and performed towards these ultimate goals. But towards this goal of realizing carbon nanotube electronics, my PhD focused on studying solution-based carbon nanotube assembly, and then developing scalable methods to align individual semiconducting carbon nanotubes across industry-relevant dimensions or across the wafer scale. So in my work to eliminate the metallic carbon nanotubes, we use a polyfluorine polymer, or PFO-BPY, which selectively sorts or wraps the semiconducting carbon nanotubes. So in this process, I combine the PFO-BPY and the raw nanotube soot, and through a series of sonications and centrifugations, we're able to achieve a highly semiconducting pure carbon nanotube ink, or polymer wrapped nanotubes in an organic solvent. In general, absorbance is used to determine the metallic content in carbon nanotube inks. Here, the black dashed line is raw nanotube soot, and the purple line is the sorted PFO-BPY wrapped nanotubes. And you can see here that in the PFO-BPY sorted nanotubes, the M11 transition peak, which is caused by metallic nanotubes, is not present anymore. However, the resolution of absorbance only allows us to say that the semiconducting purity is 99%. But a previous graduate student in the Arnold group did determine the semiconducting purity was greater than 99.98% using field effect transistors. And the purity could be even greater, but there just currently isn't a high throughput metrology technique available for this measurement. So with these high semiconducting purity nanotube inks, I then sought to align carbon nanotubes from solution across target substrates. In one of the methods I developed in my PhD, we discovered that 2-dimensional carbon nanotube liquid crystals form at liquid-liquid interfaces, and we subsequently utilized this phenomenon to transfer these 2-dimensional nanotube liquid crystals onto target wafer scale substrates. So in this process, as I discussed, we use PFO-BPY to sort and isolate pure semiconducting carbon nanotubes. And then this ink is flowed through a substrate channel suspended in a water subphase, which creates a thin layer of carbon nanotube ink at the water. The carbon nanotubes in the bulk of the ink then collect and confine into two-dimensional carbon nanotube liquid crystals at the ink-water interface. And then by translating the substrate through this ink-water interface, we can transfer these liquid crystal assemblies onto target substrates. And even without flowing the carbon nanotube ink through that confined channel, continuous films of nanotube domains with high local alignment are achieved, which is indicative of nematic liquid crystal phenomena. This means that the simple act of layering nanotube ink on water induces that concentration and collection of nanotubes at the liquid-liquid interface. These concentrated and confined nanotubes then form a liquid crystal. Within each domain of the liquid crystal, the nanotubes are well aligned, but as you can see, each domain also has a different orientation. But flowing these two-dimensional liquid crystals causes the local nanotube domains to align with the flow direction, and an exceptionally high degree of local alignment within plus or minus 6 degrees is achieved. Oh, and it looks like a question. How much does that 0.02% impurity affect viability of carbon nanotubes for some of the applications you mentioned before? So in my measurements, I didn't measure any metallic nanotubes I'm just gonna answer this question while I'm here. I didn't measure any metallic nanotubes for this high purity nanotube ink. To be able to use these nanotubes in logic applications, you would have to have like parts per billion quality of semiconducting carbon nanotubes and no metallics, you know, on a part per billion level or resolution. It could be that high. We just haven't been able to measure it. But that would be the goal concentration for logic. But anyway, for these local nanotube domains, instead adding flow to them will cause these to align with the majority direction. So we can orient all of these domains with a majority direction. And here we've been able to achieve nanotubes with a high degree of local alignment within plus or minus 6 degrees is achieved. There we go. So we also use two-dimensional fast Fourier transform analysis to quantify the variation in the local nanotube alignment angle or the local director as a function of flow rate. Shown here are SEM images with the local directors determined by 2D FFT, overlaid as these red lines. By performing this FFT analysis on multiple images from each sample, we can obtain representative director orientations through the nanotube film, as shown in these plots. Without flow, the local directors are oriented at all angles, which shows a lack of global ordering. With intermediate flow, the local directors begin to align with the majority direction, and at high flow, the global alignment approaches that high degree of alignment seen locally, where this dashed line is that plus or minus 6 degrees. These improvements in alignment and film uniformity can also be seen in these polarized optical microscopy images, where a brighter yellow indicates that the nanotubes are aligned with the flow direction, or here the horizontal, and the regions that are darker are where the nanotubes are changing alignment direction or the density is decreasing. We can see that the POM images become much brighter and more uniform at high flow rates, indicating that the nanotubes are more highly aligned across these much larger length scales. However, even at high flow rates, there are these small imperfections within the film, as indicated by these small darker domains. We found that these domains correspond to liquid crystal defects within our nanotube arrays and confirms the formation of liquid crystal assembly at the ink-water interface. Ordering within these nanotube arrays dramatically improves with increasing concentration, as you can see in these SEM images, which is indicating the importance of collective interactions among nanotubes and further evidencing lyotropic liquid crystal phenomena, or liquid crystals that depend strongly on concentration, which carbon nanotubes in bulk solution have been demonstrated to act as. Additionally, liquid crystal ordering emerges at an ink concentration of 5 microgram per milliliter, as seen by this liquid crystal defect outlined in blue. This onset is orders of magnitude lower in concentration than the onset predicted for three-dimensional liquid crystals, and is, however, consistent with the predicted onset of nematic ordering for a two-dimensional system of rods. Additionally, at an concentration of 100 microgram per milliliter, the linear packing density is around 50 nanotubes per micron, which is near the intermediate packing densities that are needed for short channel field effect transistors. We also use temperature as a route to improve nanotube ordering in these aligned liquid crystals. Here we see at 35 degrees Celsius, there are a lot of these darker defected regions in the nanotube films. However, these defected regions are eliminated almost completely at 10 degrees Celsius. SEM also shows highly aligned nanotubes mostly free from liquid crystal defects in this film. And the reason that we chose to investigate temperature is because reducing temperature increases the importance of anisotropic van der Waals interactions between messages, in this case, the nanotubes, and serves to improve order in liquid crystal assemblies. So this result, again, helps to confirm the liquid crystal assembly observed here. To prove the inherent scalability of this technique, we uniformly align carbon nanotubes across a 10-centimeter wafer piece. Shown here is a photo of the silicon oxide substrate with maps of nanotube density extracted from Raman spectroscopy that are overlaid here. Between positions 2 and 3, where the flow is well formed and steady, uniform films of highly aligned nanotubes are obtained, evidenced by the uniform color in the density map, as well as the SEM images. But then getting to actual transistor measurements, field effect transistor measurements indicate that these nanotube arrays exhibit excellent charge transport characteristics, which is a result of the high alignment formed within these 2D nanotube liquid crystals. For the data shown here, we use a silicon oxide backgate and top palladium contacts, and those are used to modulate and control the charge in the channel or in the carbon nanotubes here. So shown here is a plot of source drain current versus gate source voltage, where here, this is the on state, and here is the off state. For transistors, you want a high on state current, meaning you have a high drive current from the device. And you also want a low off state current to reduce power consumption. These transistors exhibit currents per width of around 520 microamps per micron, which correspond to 11 microamps per nanotube. Additionally, at small source drain biases, the typical on-state conductance is 1100 microsiemens per micron, which is comparable with other state-of-the-art aligned nanotube arrays. Furthermore, using a top ion gel gate, so instead of gating or controlling the charge using silicon oxide, we instead use an ion gel top gate, which allows for a better gating and better control over the charge. And so using this gating, we're able to measure subthreshold swings as small as 60 millivolts per decade, which approaches the Boltzmann limit at room temperature and demonstrates the intrinsic quality of our two-dimensional carbon nanotube liquid crystals. To characterize the uniformity of the charge transport in these arrays, we fabricated devices linearly across these 2D nanotube liquid crystals. Shown here is a subsection of these devices, here plotted on current of the device versus position along substrate, where below each data point is the representative SEM from the device channel. The SEM shows highly aligned and uniform nanotubes, which translate to uniform device on currents as well. Additionally, for all devices measured, we measure a standard deviation in device performance of only 19%, which is among the highest uniformity reported in literature for high performance nanotube transistors. These results are very exciting toward achieving the goal of highly aligned nanotubes across the wafer scale. However, actually the ideal degree of carbon nanotube alignment depends on the electronic application. So broadly, there are two regimes of nanotube transistors. One where the channel length or the length between the source and the drain electrodes is smaller than the length of the nanotube, as seen here. And the second is where the channel length is greater than the carbon nanotube length. For the first set of transistors, these nanotubes can directly span the channel length, resulting in ballistic conduction and extremely high performance, making these arrays needed for logic and CMOS applications like computers. The ideal nanotube arrays for these applications are precisely parallel, as any type of misalignment can create resistive tube-tube junctions or resistive tube-tube crossings, and those reduce or decrease the output current of the transistor. And these two-dimensional nanotube liquid crystals are fairly ideal for these short channel field effect transistors due to their highly parallel nature with few crossings. However, for the second set of transistors, the channel with channel lengths longer than the nanotube alignment, or the nanotube length, there needs to be some type of misalignment between the nanotubes to allow charges to percolate and hop between nanotubes. These long channel transistors are used in less expensive and lower performance applications such as biosensors or displays. And toward achieving these films with some degree of misalignment, most researchers use randomly oriented nanotubes because they're very easy to fabricate. However, randomly oriented nanotubes aren't really ideal for these applications either, because randomly oriented nanotubes have all of these crossings when really you only need a few crossings to allow charges to percolate. So the next part of my talk focuses on an alignment technique which results in quasi-aligned nanotube arrays, minimizing resistive nanotube junctions while still allowing charge percolation. So here we still employ the directed fluid flow as I showed previously to globally align the two-dimensional nanotube liquid crystals, but now we remove the water and instead shear or flow just purely bulk nanotube ink. So to study this, we create a sub-millimeter tall channel and force nanotube ink at high volumetric flow rates through the channel to generate large amounts of shear. In practice, the experimental procedure is similar to this. We start with a stainless steel bottom plate and place our target substrate on it. Then we define our channel using a mask and stainless steel spacers. And then the bolt holes around the outside are used to clamp the top plate to the inlet. The nanotube ink is then forced through a tubing inlet in the top plate. And first in this process, we flow the nanotube ink, followed by a bulk solvent rinse. So in our case, I primarily use nanotubes dispersed in chloroform, so my bulk solvent is chloroform. Then I rinse the substrate with isopropyl alcohol for more controllable drying, and then dry the substrate with nitrogen. So immediately by comparing nanotubes deposited at low and high shear, we can see the alignment improves with increasing shear rate. Here's a plot of the spread in alignment, or half width at half max, versus shear rate. And we can see here, so here a lower half width at half max indicates that there's less misalignment within the film, and the films are more highly aligned. So we found that regardless of how we change the shear, the alignment follows a power law with an exponent of minus 0.1, indicating that there are diminishing returns as we increase the shear rate further. Additionally, comparing the film morphology to nanotubes aligned using interfacial assembly demonstrates the importance of the two-dimensional ink-water interface to achieve that liquid crystal assembly in highly aligned nanotubes. The degree of misalignment within these quasi-aligned nanotube films do make this technique ideal for fabricating those longer channel length transistors. In addition to the degree of alignment, we control the nanotube packing density by adjusting ink concentration. We see here the packing density increases steeply until approximately 30 nanotubes per micron, when it levels off and increases at a slower slope. When we examine this point, we see that this vertex occurs once the film is approximately a saturated monolayer, and a new nanotube flowing through the channel cannot absorb on the bare substrate without overlapping previously deposited nanotubes. So this means that the film thickness and number of nanotubes deposited from this technique is self-limiting to around a monolayer. We also investigate the effect of alignment on charge transport by fabricating transistors with the alignment direction parallel and perpendicular to the mobility direction of the channel or of the transistor. So here's a typical IDS BGS curve, similar to what I showed previously, except here for parallel and perpendicular devices. And from plots like this, we can extract the slope in the linear region, which is used to calculate mobility. And we determine that the parallel devices exhibit approximately 7 times the mobility of the perpendicular devices while still maintaining a high on-off ratio. Additionally, we study the effect of packing density on transistor performance, all purely from parallel devices. And here we see the mobility increasing slowly until about 30 nanotubes per micron, which is when we expect that good percolation is achieved. We also see that the mobility saturates at 45 tubes per micron for these films. So for films with nanotubes oriented within plus or minus 34 degrees, this appears to be the ideal packing density. And then to demonstrate the scalability of this alignment technique, we uniformly align nanotubes across a 10-centimeter wafer. Shown at left is a photo of the substrate, which we have shear aligned nanotubes across. And then we characterize the film uniformity using Raman spectroscopy to measure packing density of the carbon nanotubes across the channel. Here, the white line indicates where the mask was originally, and we see no nanotubes deposited outside of the channel and a highly uniform packing density within the channel. So this result demonstrates just how scalable this technique is. But to demonstrate the utility of this technique for aligning other anisotropic structures, including biocompatible materials, we focus on aligning cellulose nanocrystals, or CNC. Cellulose nanocrystals are the basic building blocks that make up cellulose, and is an important structural component of the cell wall of various plants. In addition to large abundance, cellulose nanocrystals are biodegradable and renewable, and also exhibit a relatively high intrinsic strength, enabling them to be used in applications such as textiles or organic LEDs for passive strength. CNC can also be functionalized and utilized in biosensors and drug delivery, and also exhibit a large permanent dipole, enabling them to be used in energy harvesting and flexoelectric applications. Similar to the alignment of nanotubes with increasing shear rate, we can see the alignment increasing both in these atomic force microscopy images, but also in this plot of half width, half max versus shear rate. When we compare the alignment versus shear rate for both nanocellulose and nanotubes, we see that the nanocellulose improves more dramatically with shear rate and follows a power law with an exponent of -0.2. And so the alignment of anisotropic structures in bulk fluid is supposed to follow a -1/3 power law. So the CNC being closer to this theory than nanotubes could be due to less bending exhibited by the nanocellulose. So to summarize, throughout my PhD, I discovered novel phenomena regarding the liquid crystal assembly of carbon nanotubes at liquid-liquid interfaces, and exploited that to develop a technique resulting in highly aligned carbon nanotube arrays, ideal for high-performance electronics based on short channel field effect transistors. I additionally developed a second technique for carbon nanotube alignment, which results in quasi-aligned nanotube arrays, ideal for long channel field effect transistors. And we also demonstrated the second technique to align cellulose nanocrystals. So next, I'll very briefly discuss future work which will build on these advances in biomedical materials and electrical engineering to develop novel bioengineering devices and technologies. So the overarching goal of my future research is to develop the materials, electronics, and biointegration, and combine these three areas to achieve on-body health monitoring and highly personalized medicine. So my research will occur at the intersections of nanomaterial assembly, bio-inspired engineering, and materials and electronic design. And specific projects I will address include the development of interfacial sweat microfluidics, the development of stimuli-responsive phase and shape change materials and architectures, and the alignment of anisotropic nanostructures to create ultra-conformal electronics and biosensors. In my work, I also emphasize translation of these devices or breakthroughs to clinical testing through work with physicians and nurses, or commercialization to further prove the utility of this work and ultimately make a direct difference on improving health. The goal of my proposed research directions is to develop and combine methods for assembly, biointegration, manufacturing, and detection to measure low concentration proteins and molecules in sweat. In general, sweat is a very exciting biofluid for health diagnostics due to the ease and non-invasiveness of measurement and the rich content of biomarkers present. However, currently most on-body sweat devices are limited to studying high concentration analytes, such as electrolytes, and the use cases are primarily in establishing fitness and sweating rates. In my research, I will utilize the liquid-liquid interface to collect and concentrate analytes in sweat. This would increase detection limits and enable detection in a faster, inexpensive method. I will also develop a new realm of interfacial sweat microfluidics to enable these measurements to be conducted on body instead of in a lab. For these microfluidics, I plan to integrate colorimetric assays or electronic sensors to enable low-cost wearable devices. The second thrust of my research is to develop stimuli-responsive materials and architectures to enable personalized medicine and less invasive implants. Traditional implants are bulky, which can require large incisions and surgeries for insertion. These static implants can lead to difficulties in placement as well as mechanical and biological mismatch. In my work, I will develop and synthesize materials for stimuli-responsive implants, which allow the implant to be compressed into a smaller footprint and inserted with a small incision, and then once in place, recovered to its original geometry. The addition of drugs and the use of bioresorbable materials will also be investigated. Also, in current drug delivery, it can be difficult to avoid pre-release of drugs, which can lead to unnecessary toxicity. So here I will use phase change materials such as crystallizable oils to encapsulate drug payloads. Shown here is a two-step drug microcapsule with different drugs embedded in phase change materials, or PCMs, with different transition temperatures. So at a temperature above the first PCM transition temperature, drug 1 will be released. And then at a temperature above the second PCM transition temperature, drug 2 will be released. I plan to achieve these phase changes and drug delivery via embedding of near infrared dyes or through localized ultrasound. The goal of my final research thrust is to align nanomaterial arrays and exploit their superior charge transport and mechanical properties for flexible and wearable electronics to improve device functionality and flexibility. Compared to bulk materials, aligned nanomaterials offer improved flexibility as they allow charges to conduct even while deforming. Nanomaterials are also solution processable, which allows for extremely thin electronics to be fabricated. Specific nanomaterials I plan to align include nanomaterials, silicon, and gallium arsenide or indium phosphide nanowires as well. Toward these goals, I will align anisotropic nanomaterials using the processes that I have discussed during my PhD to fabricate films with different degrees of alignment and explore the effect of nanomaterial composition, dimensions, and degree of alignment on subsequent device performance. So to summarize, in my postdoc, I focused on improving biointegration of wearable devices for establishing a conformal but safe interface for wearable electronics in the skin. During my PhD, I worked to overcome materials challenges and fully exploit carbon nanotubes for next generation semiconducting electronics to ultimately improve devices and biosensor performance. And then finally, I outlined some next steps and future directions, which would build on this previous research to yield novel bioengineering technologies. Finally, I'd just like to acknowledge the many people who have made this research possible, including my postdoc advisor, John Rogers, and our theoretical collaborating professor, Professor Yanggong Wang, and the rest of the group of amazing postdocs, graduate students, and undergraduates that I get to work with at the Query Simpson Institute for Bioelectronics. I'd also like to thank my PhD advisor, Mike Arnold, and my collaborating professors during my PhD, as well as members of my graduate group. Importantly, I'd also like to acknowledge the funders, including the NSF, UW-Madison, and the Query Simpson Institute for Electronics, or for Bioelectronics. So finally, thank you all for your time and attention, and I can now try and answer questions.
Hey, I had a question. First off, thank you for such a great talk. That was really interesting, and I think you explained it really well. That was really fun to watch. So in the section of your presentation about your postdoc work, I know you had some plots with adhesive energy in joules per meter squared. I was just wondering, how did you measure the adhesion energy?
Yeah, so I measured the adhesion energy by essentially doing like a T-peel test of the adhesive against a silicone replica of skin. So it had like the mechanical and the texturing of skin. And then, yeah, did a T-peel test and then quantified the force, or measured the force versus the change in displacement. And then from that got the adhesive energy, or the adhesive force, and then divided that by the width of the adhesive to get the adhesion energy.
Awesome. Thank you so much.
Mm-hmm.
I had a couple of questions as well, if I can.
Yeah.
So this goes back to the crystallized oils embedded in the bulk adhesive that you mentioned, as opposed to the deterministic pattern.
Yeah.
So there you also happen to mention that it's only usable maybe twice, but once you've melted and you got the oils onto the interface between the adhesive and, at the interface of what would be the skin and the adhesive, and if you remove the oils completely, then it should go back to the normal adhesion prior to room temperature, shouldn't it? So why is it that it decreases?
No, you're absolutely correct. If you remove the oil from the adhesive, you can reuse it. Here, I just meant you can use it twice about, just because like the oil, when it first melts in these random oil crystallite composites, it comes to the interface, but not the entire adhesive interface is saturated with oil. So there is still some adhesive force, but it's not as high as it was originally in its initial case here as well. So yeah, if you did remove all of the oil from the interface, then you could absolutely reuse that. that.
So you could imagine maybe dipping it inside something on a liquid and then using that as a solvent to move the oil, and then you can use it again. I mean, you're limited still by the amount of oil you embed in the bulk, but you can potentially use it more times.
Yeah, absolutely.
Cool. And I had a second one. If you go back to the slide where you were aligning at the liquid-liquid interface and having the substrate, I guess moving the substrate to the liquid.
Yeah.
So I was just curious with respect to maybe quasi-alignment or changing alignment for the cases where you need the carbon nanotube length to be shorter than the channel length. Would it not be possible to rotate the substrate angle and therefore achieve differential alignment? So I mean, this is why I guess I wanted you to share that screen again so that I can talk about the particular rotation angle. If you oh yeah, sorry.
No. So what I'm hearing is you're asking like, why don't we rotate this substrate so that essentially between like the transistor electrodes, it would be like at an angle?
Yeah, so right now, if you imagine an axis that's normal to that substrate surface, and and then you rotate it clockwise or anti-clockwise as time proceeds. So you set up some flow, and then you deposit some nanotubes, as we see on the slide. And then after a certain amount of time, as you're lifting it up, you lift it up by a certain amount delta x, and then you maybe rotate it clockwise by however many degrees you want.
Oh, and then like deposit on the previously deposited layer? Yeah,
so if I can annotate, no, I can't annotate, but anyway, yeah, so it's so if we're looking at, say, the line of the cap, if you represent the equation of the line as, I guess, just y = 0 for them to be perfectly horizontal now, then you basically, once you lift the substrate up, and then you keep the shear direction in the same way, but then you rotate about the z-axis, that substrate, so then you end up getting maybe 1 degree or 2 degrees, however many degrees you want, by rotating that substrate, and then you can maybe have those crossings.
If so here, if I'm understanding your question correctly, so here in this technique specifically, this alignment, it's very difficult to deposit on a previously aligned film or previously aligned nanotube array, because you have to choose the contact angle, or the water chloroform contact angle at the substrate here is really important to not only achieve nanotubes that deposit on the substrate, but achieve aligned nanotubes at the substrate. So if you coat a substrate with nanotubes and then rotate it and then go back through to get that second layer, it won't deposit onto that previous nanotube layer without doing some type of surface functionalization to the nanotubes in order to modify that liquid substrate interface. Wdoes that answer your question?
Yeah. I wasn't thinking of going back over the layers. I was just thinking of having a zigzag pattern as it were. So if you have say a horizontal line, and then you end up having a sawtooth waveform or a sawtooth shape so you rotate one way, and then now you start depositing diagonally with respect to previously deposited, and then you let them deposit in that direction for a certain amount of time, and then you switch it off, and then you switch, and then you end up getting these I mean, in my head at least, these junctions or these apexes where there is enough, where it's narrower, and then you have they're closer than the usual deposition. So yeah, not going across the same thing as deposited, but along the direction, as it were.
Yeah, you could definitely do that. I think with respect to being able to lift it up, deposit this, and then rotate it and deposit it, at a different angle to the previously aligned nanotubes. I think the area, on the terms of these short channel field effect transistors, or I guess if you're asking about long channel, so for short channel, all that it's going to do is just change the alignment direction. So instead of it being perfectly parallel, it's going to make it, a little bit angled here. For longer channel transistors, which have, wider dimensions in both channel length and width, I think you could visualize something like that to enable like very localized, like direction changes. But I think it would be so localized, and also you might not end up getting as many crossings as you would need for those long channel transistors, just because it would be still very small in that area that you're changing the direction across, would be my guess, if that answers.
Thank you.
Yeah, thanks for your question.
Erica, you want to ask a question?
Sure. Ellen, did you say Erica? Just to make sure I
Yes.
heard you. Okay. I put it in the chat, but I was curious, have you ever done your adhesion tests on animals or cadaver skin? Looking at the effects of the adhesive and the removal of the adhesive on the skin. And I'm wondering how much of the problem of the skin irritation that you're going after is due to the actual removal and the removal or the adhesive strength, and how much that's due to actually the type of adhesive or the amount of time the adhesive has been on the skin.
Yeah, so with respect to, I have done adhesion measurements on porcine skin to compare, and the adhesion is, yeah, it's very similar to on porcine skin, as long as you remove, you know, the oils from the pig skin, which can be a little bit difficult. But I think in general, the things that cause, you know, skin irritation when you remove adhesives from patients, I think there have been some studies that have backed this up, but it's essentially like, you know, how you're peeling it with respect to also the adhesive force. So what's the adhesive force, and then how are you peeling it? Are you trying to peel it from the edges? Are you trying to like lift it up off of the skin? And so I think having it peel from the edges and then having this reduced or this, you know, method to reduce the adhesion improves that with respect to like reducing that relative force that the skin undergoes. I don't think it has to do directly with the amount of time that the adhesive has been in contact with the skin. It more just has to do with like that adhesive force that is exhibited, would be my understanding. Does that answer your question?
Yeah, it does. Thank you.
Okay, thank you.
Feel free to laugh out loud at this because I'm so far out of my safe space that it's might be ridiculous, but all of this is screaming startup commercialization to me. How close are these techniques and technologies to actually being useful in practical medicine?
In terms of like the first, like these adhesive oil composites?
No, actually, I was thinking about the
nanotubes?
marshaling the nanotubes in various arrays and directions to make transistors.
Yeah. So with the nanotubes, for logic and RF, like with the short channel transistors, with the liquid crystals, I think we're probably, in terms of where the nanotube field is at, I think the field still has work to do before it can be actually integrated into logic and RF, because it does need to be exactly parallel. And we still have misalignment both in these films and in other techniques in the literature. So with logic and RF, I think that this is, you know, a little bit far, but there have been, we did collaborate in my PhD, we did collaborate with a startup out of California focused on RF transistors of nanotubes, and they were able to make, you know, the highest performing RF devices based on nanotubes, which far exceeded silicon. So there is like a lot of work being done towards that, but it just has more hurdles in terms of achieving precise alignment. With respect to the longer channel transistors, I think those, these films that we have, like I think that technique is like perfect for industry in terms of it's exceptionally scalable. You don't have to worry, you can really harvest the ink and reuse it. There's no like loss of material really in that technique. So I think with respect to that, I know that some of the people, or one of the students in my group, or in my old group, the Arnold group, has been looking at starting a startup for that process. I don't know how far along they are in that process, or you know, if it will come to fruition, but I think that technique is a lot closer to being able to make a large difference on electronics.
Thank you.
Another thought just popped into my head. Can you combine both of them? So with your patterned deposition of the phase change material which are melting, and then basically it's melting through those regularly patterned arrays. If you suspend carbon nanotubes in that liquid and then melt it through, so it's like a sieve, and then you can deposit them vertically aligned, maybe.
Yeah, that would be really interesting to investigate something like that. Yeah, I hadn't thought of like combining both of those areas, but yeah, that would be really interesting to envision that collection of those two areas to achieve.
That would probably then, I mean, you probably think of what vertically aligned or arrays of vertically aligned nanotubes, which have at least some applications that I'm aware of are they use them. I mean, I'm not claiming that this is how they made them, but arrays of vertically aligned nanotubes are really good absorbents, so they're really good black body absorbers, and then they've been used in radiometers just to absorb pretty much everything that's been incident on them. So that's happening actually theoretical aspect, but yeah, it just crossed my mind that you could combine both of them. Probably not really feasible. I don't know. But
yeah, it might not be feasible. Just in terms of being able to achieve that really precise vertical alignment and yeah, achieve that like across a large area. But I think that would be a really interesting, combination. And that's something that would definitely be an interesting route to go down for sure. And like you said, there are definitely applications where vertically aligned nanotubes are, very in demand for sure. Yeah, so thank you for that comment.
Yay, thank you. I think it was good. Appreciate it.
All right, thank you.
Perfect. Thank you so much.
Yes.
Thank
Is
you.
that
That
the-
was wonderful.
Okay, thank you.
Yeah.
So great to talk with you all. Thanks.
Katie,
Oh.
maybe just briefly humor me.
Mhm.
How much are you working with doctors to shape the direction of your work for specific applications? And how much are you focused just on the adhesive properties? Do you know what?
Yeah, so essentially, this project started because of talking to one of the doctors that's part of QSIB, and talking to John, my advisor. Like both of them were saying, they go and they do these like deployments of devices onto babies, and they see the skin, start to peel, not like rip, but like you can see it start to tension, and it's there. Yeah, they were like, this is definitely a big problem in this field. So really talking to and getting advice from the doctor that I work with here helped motivate the project in terms of like testing on adults or on babies. This is just I've just been primarily optimizing the adhesive force. So we haven't done any tests on babies at this point, just because I think that this work, it was needed to demonstrate the technique and demonstrate the application and able to achieve this adhesion reduction, and then the next step would be deploying it. But it overall, yeah, being guided by doctors and nurses. The Rogers group is really, and my future research really takes that into account for sure.
Thank you so much. I really enjoyed it. I appreciate it.
Yeah, thank you so much.
Really,
If it's possible, this is,
yeah, Chris.
this is Chris. I apologize. I'm in transit, and so I'm not on camera, but I was able to listen. And I also, I missed the very beginning of your talk. I apologize for that. So I had a bit of a blind spot or a deaf spot. But I do want to say I'm very impressed, and I've had significant background, particularly in the last 10 years in digital health kind of generally, and in particular, wearables. I mean, even so much so that I had meetings with the digital czar of the FDA on exactly this, and got to meet with his team and ask all sorts of dumb questions with respect to a prototype that we were working on. And anyway, the punchline is it's a remarkable field. And when I saw just the wearables theme in the and in the announcement for your presentation, I really tried to clear the deck so I could attend it. And will there be a recording where I can see the beginning as
Yes.
well?
Yes.
Yeah.
I was yes.
Yeah, because this field is just so strategically important, you can't overstate it. And so the long-term thing, based on a lot of the thinking that we've done for strategy and investing reasons and otherwise, but I mean, the whole realm of non-invasive personalized medicine is the future, right? And it may be closer than we think, but so I think that's remarkable. And then also, I've just personally been working with a startup for a while, and they're doing basically digital acupuncture, and they're using a patch to basically tap into the human nervous system, which is really a deep learning system. It's the OG deep learning system, biology. And in some of their initial applications of things, like they've actually been able to control overactive bladder.
Oh, really?
Yeah, sleep apnea, all sorts of things. But the net of it is, I mean, all the semiconductor discussion that you went through was really remarkable. And also, I resonated with that. And in particular, the startup I'm referring to, these are microprocessor experts, and they sort of drifted into this field as an application. So what's interesting about that is I could kind of go on, but I'm really impressed with your presentation and also the level of detail that you've taken this to, and the whole notion of a topical patch that is the interface to the actual biology, both in terms of diagnostic and therapeutic applications, is huge. So anyway, if there's some way to just kind of follow up on the to review the presentation again, or even get a copy of it, that would be remarkable.
Yes, I will send that to you.
Yeah, Chris, we record all the colloquia,
Yeah.
and Ellen has them all online for free. No, just go to our webpage, www. Katie, Chris comes from a considerable position of depth and experience in industry. He was advisor to the CEO of Samsung for 5 years, so I would listen to him.
Yeah, I really appreciate your comments, Chris. And yeah, I'm really excited about wearables in general, for the reasons that you stated. And I think it's an area that really, there's so much promise and, so much potential, and we need just to work on it and like exploit those, devices and develop those interfaces more to achieve that.
Yeah, no, it's huge. It's anyway, I was very impressed. I really appreciate the presentation.
All right, Katie, we'll let you go on a Friday afternoon. Go take the rest of the day off. Thank you so much for making it on our time schedule. Appreciate it.
Yeah, thank you all.
Thank you.
Bye.
I might.